All right, everyone. Welcome. My name is Haochen. Today I'm presenting our latest work on the model context protocol servers for science and HPC. So right now, if you want to build a large language model powered agent, you kind of want to let your LLM to leverage some outside to connect to the outer world, like all the local, either your local file systems or all the different kind of services. The usual way of doing this is through something called model context protocol. To do that, you probably can find a kind of MCP server already being implemented by someone or open sourced and expose certain tools for your large language model to use. Or if you can also build a Sing HTTP wrapper around some kind of SDK of Slack or of other apps to build your own Sing MCP server. And in this heterogeneous research infrastructure, which has different ways to submit a job, different way to interact with all the storage servers, we don't want to build everything from the ground up, everything. So how about just use existing global services to support this kind of workflow? So we build MCP servers for compute by wrapping around the compute SDK to support tools like list my endpoints, register Python function, register shell command, submit task, get task status. We also build MCP for transfer, which has tools such as submit transfer tasks and get task events. And then we also have MCP for search and also Garden, built by the Garden team. And so here's one case of we're trying to use the MCP servers and a large language model to do something simple in a quantum chemistry world. So all the interactions start with user sending something, sending a list of message, which is called a prompt. So this prompt has three parts. The first part is saying, hey, I have a Globus compute endpoint available at some UID, and it has some packages already installed. And so can you optimize the structure of the 6 molecules and calculate some energy gap of the molecule, some kind of a metrics. And here are the names of the 6 molecules and what do they look like. So the first step the large language model figure out to do is call the register Python function tool inside the compute MCP. And it's able to figuring out some kind of a simple workflow, like here is to run the optimization, and here is to calculate the energy. So the next step after having this kind of Python function, it calls the submit task to really submit to the Polaris and then waiting for all the tasks to complete. So because we are calculating some kind of energy gaps of all the 6 molecules, so it submitted 6 times and we return 6 UIDs. And after that, the user sends something like, can you visualize the results? And as a result, it's able to give us a summary table of all the molecules and all the energy gaps, as well as some kind of a interactive visualization panel. You can use your mouse to hover over to see those values. And the second workflow is about multi-site biology workflow. The prompt is fairly long. Probably you cannot see them very clearly. But the first part is saying, hey, here is my endpoints, and here are some user directories. The second part is what are the packages are available, and it gives a list of 8 steps to run. And I will explain that later. And the last part is about some input parameters. Here are the species, the input seed for this workflow to kickstart the workflow. So the first step is about checking whether the facilities are online. And this is done by the large language model is able to call the facility, our facility MCP to check whether the services are online. And then the next step is to download the data. And it's again done through the 3-step process, register Python function, and something like here is the search query. And this search query is actually provided by the user somewhere here. And then download the data, fetch the data. And the next step is to run some kind of sequence alignment using register Python function, submit task, and get task status. What's more is transfer the task from Polaris to NERSC through calling our transfer MCP, specifically using a tool called submit transfer task and get task events. And the next step is to really run the algorithm to build the trees using the same compute MCP tools. And the visualization comes back, as you can see, probably there are 2 trees. And we can see, indeed, they follow the user instruction of using this package to run on Polaris, and also another package to construct the tree run on NERSC. So that's the visualization result. So here are some key lessons we learned in this kind of exploration process. Currently, because MCP framework is a rather rapidly evolving framework, it doesn't really support the OAuth-based authentication protocols really well. So here we advise the user just to host their MCP servers locally with the cloud desktop, with all the host the MCP servers locally in a trusted environment to use the standard practice of the Globus auth to manage tokens. But in the future work, we want to explore different authentication methods to really support something hosted multi-tenant MCP deployment. And the second key lesson is something about resilience. And this is a snapshot of the biology workflow. And in one step, it finds out, hey, the tree reconstruction really fails because it cannot find certain packages because certain command was not found. So we start to try it with different commands. So we see the agents have some ability to self-correct themselves, but we want to explore more strategies to make sure the workflow finish resiliently and smoothly using technique for error recovery or maintaining consistency across tasks. That's our next step we're gonna explore. And here is our preprint and also the QR code to the slides. It has all the transcripts. So thank you for listening.